Okay, chapter 12 is on trig equations and their identities. We spent a lot of time working with trig now, both solving triangles geometrically, talking about the unit circle and how things rotate, sines and cosines, graphing sine and cosine and tangent, all this stuff. Now we'll take some trig equations, which means something like this, and solve them. I know that's very basic, but we're going to get much more complex as we move forward. Our ultimate goal is just to be able to solve any trig equation at any time, and to be able to use them to model repeating behaviors, periodic actions and motions. Let's talk about, here's our unit circle again. Let's say this right here is the point 0.6, 0.8. So you remember the unit circle is all within 4 square units. Like, this is us being really far zoomed in on a grid. Is the point 0.6 comma 0.8 on the unit circle? Like, are these actual coordinates on this circle or not? Well, since we know the unit circle has a radius of 1 unit, we know that this length here plus this length here, when we do the Pythagorean theorem, should come out to 1. I know that if 0.6 squared plus 0.8 squared equals 1 squared, so really if 0.6 squared plus 0.8 squared equals 1, then this point is on the unit circle. Well, 0.6 squared is 36 hundredths, 0.8 squared is 64 hundredths. Those put together do give us 1, which means that this point is on the unit circle. What that also means is every single point on the unit circle, if I ran its Pythag, would come out to 1. But remember that with these coordinates, the x value could be thought of as the cosine of some angle, whatever this angle theta is, and the y value is the sine of that same angle. So that means that if I had cosine of theta squared plus the sine of theta squared, that should come out to 1 every single time, which it turns out it does. Like right now, I don't know if my calculator is in radians or degrees, and I don't care. If I do the cosine of 23 squared, or just 3 apparently, plus the sine of 3 squared, in radians or degrees it makes no difference. This is going to come out to 1. This right here is called a Pythagorean identity. It's a very important one. It's called the Pythagorean theorem, or the Pythagorean identity, because it clearly comes from the Pythagorean theorem. An identity, you probably remember, is something that is true. And we saw them a lot with our basic algebra. Like the additive identity was 0, because the identity is true, and it's something that doesn't change anything. If I add a 0 to something, nothing changes. If I multiply by 1, nothing changes. And if I do the identity matrix times something, nothing changes. I'm not writing that well, so we should move on from this. So this is called the Pythagorean identity. I could actually take this identity and play with it a little bit. If I take cosine and sine in 1 and divide them all by cosine, or by cosine squared actually, this gives me the new identity, 1 plus sine over cosine is tangent, 1 plus tangent squared, 1 over cosine is secant, so 1 plus tangent squared equals secant squared is an identity. Or, instead of dividing everything by cosine, I could divide everything by sine. And that gives me cosine over sine is tangent, so that would become tan squared, no, cosine over sine is cotangent, excuse me. Cotangent squared plus 1 equals cosecant squared. These are 3 Pythagorean identities. They're all showing the same relationship. They're all just a manipulation of the first one. But here's 3 Pythag identities. I have them listed out right here. Don't forget these reciprocal identities, that cosecant is 1 over sine, that secant is 1 over cosine, and that cotangent is 1 over tangent, which really makes it cosine over sine. So these are identities that we can now use to simplify trig expressions. This trig expression right now is kind of a mess. I'm wondering if I can make it any simpler. So I'm going to simplify this by using some trig identities. Let's start with this. I know that tangent is sine over cosine. I know that because that is a reciprocal identity. I'm going to off to the side write out which identities I'm using to justify my steps. That's a reciprocal identity. Well, now if I just do some algebra and multiply, this becomes 1 minus sine squared, and the cosines cancel. Now, 1 minus sine squared isn't an identity that I'm given right away. But if I look over here at this one, I can manipulate this identity. Like if I subtract sine squared from both sides, that gives me cosine squared equals 1 minus sine squared. So 1 minus sine squared is the same as cosine squared, so this 1 minus sine squared I can just call cosine squared. And I have simplified the trig expression. So you're going to get really familiar with the fact that yes, sine squared plus cosine squared equals 1, but that also means that 1 minus cosine squared is sine squared, and 1 minus sine squared is cosine squared, like we have here. So I simplified this to something that's actually much, much cleaner and prettier, and that's quite nice. So this step from getting from here to here was a Pythag identity. Okay, let's simplify this one. Tangent, I'm going to call sine over cosine. Cosecant is 1 over sine. So that was definition of tangent and reciprocal identities. The sines cancel when you multiply. So this becomes 1 over cosine. That's just algebra. I don't actually need you to write algebra each time. Just do the math. 1 over cosine, we know, is secant. That's another reciprocal identity. Simplified that one. So simplifying trig expressions is just finding identities or finding things that we know are true or being able to cancel things to write some trig expression in something that is clearly better. To be simplified, you need to have everything written in its simplest terms, obviously, but if possible, your goal is to get it down to one trig function, or at least the same trig function appearing over and over and over. So if we can get like just secant or just secant squared, that's our goal. It's not always possible, but try and get it down to one trig function as simplified as you can without multiple things appearing and without pluses and minuses and divisions if possible. So like don't ever leave it as 1 over cosine. That's got division. We don't want the division. We just want secant. Now usually when I do these types of videos, I give you some time to say, okay, think about how you would simplify these, or try to simplify these on your own. And that gets pretty difficult with this stuff because it's so new. So I'm just going to kind of go through these and show you some strategies. Here, cotangent I know is sine over or cosine over sine. So if I wanted to, I could take cotangent squared and make it cosine squared over sine squared. But I also think I have a Pythag identity with 1 plus cotangent squared. I believe that 1 plus cotangent squared is cosecant squared. I'm going to check real quick. It is. So I'm just going to take this 1 plus cotangent squared and turn it into cosecant squared. And I can do that because of it's a Pythag identity. Okay, now you notice how I just scrolled up and down real quick? I don't want to do that over and over, and you don't want to do that over and over. So I very, very strongly recommend you grab an actual sheet of paper, an actual like note card, and physically write down all the identities. and then you can just refer to them on your note card really quick, and it'll save you a lot of time because you're going to have to look at them a ton until you start to get them memorized. The best thing to do is just get them memorized, but that can be difficult. So I really recommend that you write down the identities as you add them. We've done 6 right so far. We're going to add 3 more in this video. Then we just keep doing identities over and over and over for video after video after video. So write them down. Okay, cosecant, I know, is 1 over sine squared. And that's just a reciprocal identity. One of these sines cancels one of these sines, so we get 1 over sine theta, which is just cosecant theta. And that is a reciprocal identity again. Okay, here's the first one that's got messy fractions for us to deal with. I need to get a common denominator so that I can add or subtract fractions. So the common denominator here is cosine sine. I don't say the theta every time. You don't have to either. It is cosine theta sine theta, or it could even be cosine x sine x. Doesn't matter what that variable is. But it's cosine sine. So I'm going to multiply this side over here by cosine over cosine, and the one on the left by sine over sine. And that's going to give me sine squared over sine cosine plus cosine squared over sine cosine. All that we've done so far is just algebra that doesn't need justifying. But because I have a common denominator, the numerators can combine. And we know that sine squared plus cosine squared is just 1. Okay, this is a Pythag identity. Sine squared plus cosine squared is just 1. Well, 1 over sine is cosecant. 1 over cosine is secant. That's as far as that one's getting. So like I said, I would love to be able to write this as a single trig function. This one can't, and that's okay. I think you'll agree that cosecant secant is far simpler than sine over cosine plus cosine over sine. Now we could have taken sine over cosine plus cosine over sine and turned that into tangent theta plus cotangent theta, because that's what sine and cosine are. But I much prefer a multiply than a plus, as will you once you start trying to solve. Solving with multiplication is way, way simpler than solving with addition, because you just need factors. So if you can get rid of the addition and make things in terms of multiplication, it's far superior. Okay, this last one, my hope is at this point becomes fairly straightforward and simple and obvious. Sine, cosine, tangent, cosecant, secant, cotangent. Those are all 6 of our trig functions being multiplied. But sine and cosecant are reciprocals of each other. That's sine times 1 over sine. Those are going to cancel. Cosine and secant are reciprocals of each other. Cosine times 1 over cosine. Those are going to cancel. And you probably see where this is going. Tangent and cotangent are reciprocals of each other. They're going to cancel each other. That becomes 1. That becomes 1. That becomes 1. This is all just 1. And that was all because of reciprocal identities. So the point here is if you have sine theta times cosecant theta, because they're reciprocals, we just know that's 1. You can just knock that one out real quick. Sine times cosecant is 1. So if you took every trig function, multiplied them, because they're all reciprocals of each other, they cancel to become 1. Okay, let's add 3 more identities. They're called the negative angle identities. If you have the sine of a negative theta, it's the same as a negative sine of theta. Let me try and explain what that means. Suppose here's some angle theta. And this point right here we know is cosine theta sine theta. xy. If I wanted to find the sine of negative theta, well, sine of negative theta would be this. the x value isn't going to change, but the y value switches. Okay, so notice how this x value here matches this x value here. Like these are at the same spot on the unit circle. So if you're doing a negative angle is just a reflection over the x-axis. Theta, negative theta. That means the x values don't change. Cosine theta is the same as cosine negative theta. That's what this is saying. Cosine theta is the same as cosine negative theta. We write it the other way around. Cosine negative theta is the sine of theta. If you switch the direction of the angle, the x value is not going to change, but the y value flips. The y value here was positive. This is going to be the same y value, but negative. So the y value is switching. That is why the sine of a negative angle is the same thing as the negative sine of the initial angle. The x value doesn't change, the y value switches. That's what we're saying here. Then we remember that tangent is sine over cosine, which means that if I did the tangent of negative theta, I would be doing the sine of negative theta divided by the cosine of negative theta, which is then going to be, well, the sine of negative theta we know is negative sine theta. The cosine of negative theta we know is just still cosine theta. So this is negative sine over cosine, which is negative tangent theta. That's that identity. It's just about what happens if you reflect an angle. That's all this is saying. Turns out if you reflect an angle, the y value switches, the x value stays the same, so the ratio of y over x, the sine over cosine, also flips to become negative. So I'm going to use that to verify this identity right here. Now verifying is different than simplifying. With simplifying, we're trying to find what the actual result is. With verifying, we are told the result. I am told this is going to come out to cosine squared. I have to make it happen. Well, I first see right away, oh, here's a sine of a negative theta. That's a negative angle identity. I know that'll become negative sine theta. So I can write this as 1 minus negative sine theta times 1 minus sine theta. I'm just going to manipulate the left side and not touch the right side. Well, 1 minus negative sine theta is 1 plus sine theta. 1 plus sine theta times 1 minus sine theta becomes 1 minus sine squared theta. If you're not sure how I got that, take a second and actually FOIL 1 plus sine and 1 minus sine. They're a difference of squares, so you get 1 minus sine squared. And 1 minus sine squared is a Pythag identity. We know that's cosine squared. I'll show that because remember, sine squared plus cosine squared equals 1. Sorry, I sometimes forget to write the theta because I don't say it. If I subtract a sine squared from both sides, I get that the cosine squared of theta equals 1 minus sine squared theta, and that's what happened here. So this was a negative angle identity. These two steps were just algebra, and this was a Pythag identity. I've now shown that this is true. It does actually equal cosine squared. I verified the identity. Verifying is the last piece we have for this. There's verifying versus simplifying. If you're verifying an identity, you're trying to show that one side is equal to the other. You cannot do the same thing to both sides of the equation. So I can't try to, like, in this problem down here, I'm never going to try to add cosine of theta to both sides. You can't do the same thing to both sides because then you're not verifying, you're just sort of manipulating. I want to show that this is the same as this. I don't want to show that, like, tan theta sine theta plus cosine theta equals secant theta. That's not what I was asked to show. You might wonder, well, why does that matter? Don't we know by the additive property of equality that these things are going to be the same? Yes, but the division property of equality doesn't exist. And the multiplication property of equality causes real problems if you're multiplying by 0. And sometimes with cosine theta, you have a 0 and you don't know it. So we just can't be using, we can't do the same thing to both sides of the equation. So whenever you're verifying, you can't do the same thing to both sides. So you manipulate one side. If you want, you can do the two sides independently, but you can't take one thing from one side and put it on the other. If you're simplifying or verifying trig identities, here's the processes you should use. You should always start by looking for a Pythag identity, or at least for the potential for a Pythag identity. If you see something being squared and added, or if you see a 1 in a subtraction or an addition, it's pretty likely you can use a Pythag identity. So look for that. Write everything in terms of sines and cosines if possible. Get a common denominator if you have fractions being added or subtracted. And we haven't done any factoring yet, but sometimes you might have to factor. And that can be a big breakthrough for you. So I'm going to try to verify that this side is the same as this side. On the left side, I'm going to take tangent and just turn it into sine over cosine, which I can call sine squared over cosine. That right now is the only thing that jumps out to me that I could do on the left side. So I'm just going to do that on the left side and stop. Now I'm going to play with the right side. If I can make this look like any of these three things, I have done my job. So I'm going to start by saying that secant is 1 over cosine, and that's a reciprocal identity. Then I'm going to get a common denominator. So the common denominator here is cosine. So I'm going to multiply the left side by nothing and multiply the right side by cosine over cosine. That gives me a cosine squared over cosine theta. If you want me to show that step, I can, but these things have so many steps sometimes that we have to just trust that you and I can read algebra and understand, oh yeah, getting a common denominator by doing 1 over cosine over cosine. 1 minus cosine squared is something. 1 minus cosine squared is sine squared. And now I've got it. Look, these two things are the same. So I can now just take the steps that I have in pink and write them backwards. Like, I now know that since I have sine squared over cosine, well, I know sine squared over cosine I can just think of as sine over cosine times sine. And sine over cosine I know is tangent. And boom, I've proven it. I've verified that secant minus cosine can just become tangent sine. And I did that by just manipulating the right side of the equation. I used the left side to give me some targets to shoot for, but I didn't actually use anything on the left side and move it over to the right side. I just knew that if I could make the right side look like any of these things, then I've done my job. It doesn't always have to be manipulating the right side or the left side. Just do whatever you have to do. There's no rules about that. Just don't do the same thing to both sides of the equation and show that one side equals the other. Okay, a lot of stuff covered today. An identity is a basic, true statement about something. Trig expressions can be manipulated and rearranged using mathematical processes to be put into more helpful or familiar forms. And when you're trying to simplify or verify identities, look for trig, Pythag identities, write things in terms of sine and cosine, find common denominators, and factor, typically as a last resort, or if it's totally obvious because like you have a difference of squares somewhere. When you're verifying identities, you have to work with sides independently. Next video, we talk about sum and difference formulas. What happens if you have an angle plus an angle inside of a function? See you then. Okay, check this out. I've got two circles set up, but I'm going to have one of them spin faster than the other. This might be tough for me to get going, but here we go. I want to animate this point. Go. Animate. Start. Display. Animate. Resume animation. Okay, that's not it. I want this point to go faster. There it is. The point on the bottom right is going faster than the point on the top left, but they're both rotating around the same size circle. The point on the bottom right is going around 4/3 times faster than the one on the left. And it makes this kind of cool looking spirograph sort of thing. And it's like, looks like it has 3 dimensions, like it's just a bunch of rotating lines, like a physics, looks like a model of an atom maybe. But whoa, there it goes. For some reason it makes me hungry. I can't explain why that is, but I think most things make me hungry. Just so you know, if you like these videos, I got a lot more. They're covering Algebra 2 Trig. I also got worksheets and curriculum and homework sets and all kinds of things you can look at. There's a link down below in the description. But this is pretty great.